In this section, we're going to talk about null space, column space, and what those mean, how they're related to each other, how we can find those things, and most importantly, we're doing it because these are subspaces, and we just talked about subspaces in the last section, and so that's why this section follows the last section. And again, it's an application, two different applications of what a subspace is, and they're properties or sets that end up being fairly important for linear transformations and matrix algebra in general. And so the first so the first two things are listed here. I just dropped my pen and lost my train of thought there for a second. So we see subspaces in usually two ways. As the solution sets to systems of homogeneous equations. So remember, the word homogeneous means that we're solving a system that looks like ax equals 0. And so it's the 0 part of this that makes it homogeneous. And so solutions to this system are in the null space. And so that turns out to be a subspace of a vector space. Or sometimes we often see them as the sets of linear combinations of certain specified vectors. And the specified vectors that we're going to talk about are the columns of matrices. And so this is where we're talking about column space. And so we're going to start with the null space on this page and then take a look at the column space on the next page. So let's take a look and see what the null space is. So the null space of an m by n matrix, so m by n, so it doesn't have to be square necessarily. The shorthand notation for this is null A, so you'll often see this in books and in homework problems and things like that. Null A means the null space of A. So the null space of a matrix A is the set of all solutions to the homogeneous equation ax equals 0. So all the solution sets of that equation, all the solutions are in the null space. And so here's how we could write that using set builder notation. This says null space of A is all x such that x is in Rn and ax equals 0. And so if you're not familiar, let me just write that down in case you're not familiar with this. This is the kind of notation you might see in like a proofs class. And if you haven't taken a proofs class, you might not be super familiar. So you would read that as all x such that, the such that part is the colon, means such that x is in Rn and ax equals 0. Here's what that looks like visually. So if this is our domain, this might be the domain of A. If this is a linear transformation, it'd be the domain. And this might be the range of A. We've seen this graph or this image a couple times now. And we know that A is m by n, right? And so if you're going to multiply something by A, right, if you're going to multiply x on the right side of A, like ax, for example, the inside dimensions need to match. And so that means domain has size n. And so the domain of n has dimension n. And then it gets sent to things that are size m, because the number of rows will tell us the size of the output, right? And so the range then has dimension m. And so that's why, for example, in this definition, it says that x is in Rn. So A is m by n, and so that means things that you multiply by A are size n, and things that you multiply by A are in the null space, right? Or I should say you multiply things in the null space by A to send them to 0, and so that's why those things are size n. The other thing you should see in this particular picture is that the null space of this particular arbitrary, whatever A is, we don't know what the matrix that represents this is, but it's saying that everything along this line is in the null space because everything along that line, notice, is getting sent to the 0 vector in Rm. And so I'd like to make that note. So this is saying the null space of A in this image is the entire line being shown. So is the whole line, because A is sending the entire line to the 0 vector over in the range. So I'd like to write just a few of those things down in words too. I know I've said some of these things, but I want to just, there's room here, so let's add a few words here. So the null space is going to be the set of all vectors that the matrix A sends to the 0 vector. And so this is a linear transformation represented by A. Then it would be everything that the transformation sends to 0. If it's just an arbitrary matrix A, it's just things that you multiply by A to get the 0 vector. There's another word for that called the kernel, and you sometimes see that in the homework especially, and so null A is sometimes called the kernel of A. And so just be aware that that's another notation for that, and again, you do see it occasionally, especially in the homework. Sometimes that's abbreviated like KERA, that would be kernel of A. And so if the null space are all the vectors that get sent to 0, we find the null space by solving the homogeneous equation, AX equals 0. And so to find the null space of A, you want to solve the homogeneous system. AX equals 0. And we talked about solving the homogeneous system in a previous section, and so we're going to obviously do some examples here, but if you want a refresher on that, we covered solving the homogeneous system in section 1.5. If you remember, we get non-zero solutions to this if we have free variables. If we don't have free variables, then we only get the trivial solution. Okay, so that's what the null space is. It's all the vectors that get sent to 0. We therefore solve it by, or find the null space of a matrix by solving the homogeneous equation. With that in mind, it's like very, very easy to figure out if a vector is in the null space. So like the example at the bottom of the page here is just showing us when a vector is in the null space. So let's let A be the matrix in 2 above. And so in this particular, I took this from the textbook. The matrix A, there's no 2 above. So the matrix A is 1, -3, 2, -5, 9, 1. And so if this is our matrix A, the question is U in the null space of A? And so if it is, we should be able to multiply U by A and get 0. And so if you want to test for something being in the null space, just multiply it by A and see if you get the 0 vector. And so here I am multiplying A times U. Here's the matrix A multiplied by U. And when we do that, we see that we get this, and those numbers add up to 0, 0. And so U is in the null space, just to be clear, since we multiplied U by A and we got the 0 vector. So very easy to test if something's in the null space. Just multiply it by A and see if you get the 0 vector. Okay. So this has to do with subspaces using the theorem on the next page. So let's look at that theorem. Let's read the theorem here. So it says the null space of an m by n matrix A is a subspace of Rn. Okay, so here's the word subspace, and we're saying Rn specifically. And so as a quick reminder here, if A is m by n, the m part tells you the size of the range, the values in the range, and the n tells you the size of the vectors in the domain. And so you multiply things by A to send them to 0, right? And so the things you multiply by are in the domain, and so that's why the null space is a subset of the domain, which is in Rn. The other way to say that is, equivalently, the set of solutions to the system AX equals 0, so all the solutions to this thing of m homogeneous linear equations in n unknowns is a subspace of Rn. So again, it's saying that the null space is a subspace of Rn. And so I'd like to prove that real quick. Let's show that the null space is actually a subspace of Rn. And so in order to do that, we would need to show the subspace properties, which we had seen in the last section. So let me just remind you what those 3 things are. So from the last section we saw in order to show something's a subspace, it needs to be a subset of a vector space, and then we need to show these three properties. And so the null space already is a subset of Rn, so we just need to show the three properties here. Right? So the null space already are the x's in the domain, right? And so these are a subset of Rn, which is a vector space. Right? We showed in the last class that all Rn are a vector space. And so since we already have a subset, we just need to show the three subspace properties. And so as a quick reminder, the way we show the three subspace properties is we pick two items in the space. We pick a u and a v in the space, and then we show that 0 is in our space, the sum of two vectors stays in the space, and scalar multiples stay in the space. And so let's pick two vectors in our space. So let's suppose, and our space is the null space, right? So let's suppose vectors u and v are in the null space of A. Well, by definition, if they're in the null space, they get sent to the 0 vector. And so this means that A times u equals 0, and A times v equals 0. And so this is an important relationship that we're going to use throughout the three properties. And so the first thing we need to do is to show the 0 vector is in our space. So we want to show 0 is in the null space of A. Well, if 0 is in the null space of A, that means that when you multiply it by A, it gets sent to 0. Right? That's the definition of the null space. And so let's take A and multiply it by 0. Well, we know that when we multiply anything by 0, we get the 0 vector. And so look, 0 is in the null space because when we multiply it by A, we get the 0 vector. And so yes, 0 is in the null space of A. So property 1 is satisfied. Property 2 says we should be able to show that u plus v, when we add two arbitrary vectors, that it's in the null space. Two arbitrary vectors that are already in it separately, right? So u and v are in the null space separately by assumption up here, and we know that this is true. So let's show that the sum is also in the null space. So let's take u plus v and multiply it by a. And we want to show that that equals 0, right? Well, we know we can distribute the matrix through the sum of vectors. And then we know that each one of those individual things equals 0, right? So this, from the property up here, we know that this equals 0 and that this equals the 0 vector. And so we just got 0 plus 0, which is 0. And so that one worked too, right? U plus v is also in the null space because we multiplied u plus v times a, and we got the 0 vector. And so it's in the null space. The third property says to show that a constant times a vector is in the null space. So show c times u is in the null space of A, where c is some arbitrary scalar. And so let's take c times u and multiply it by a and see if we get 0. So a times cu, well, we know that this is just a constant, and so you can pull constants out in front of matrix multiplication. So that's going to be c times au. Well, we know au is 0. So this piece equals 0, the 0 vector. And so this is just c times the 0 vector, which is the 0 vector. And so that one worked too. And so yes, cu is also in the null space. And so we showed all three properties are satisfied. And so we have shown that all three properties of a subspace are satisfied. And so we've showed that the null space is in fact a subspace of Rn. Cool. So that's what the null space is. It's all the vectors that get sent to 0. you solve the homogeneous equation to figure out what it is. The next part of the chapter is talking about the column space. And the column space has some similarities in that it's a subspace. There's some similarities to the null space, that is, but it's also quite different as well. And so let's take a look at the column space and figure out what that's all about. Okay, so let's read this definition. The column space of an m by n matrix, so again, not square necessarily, we denote that with col A. So when you see col A, that means the column space of A. And the column space is the set of all linear combinations of the columns of A. And so if A is a bunch of columns, A1 through AN, then if we're doing all linear combinations of those columns, that's also known as the span. And so the column space is the span of the columns. In other words, let's write out what that means. That is, the column space of A equals all vectors of the form x sub I such that x sub I is a linear combination of the columns. So C1A1 plus C2A2 plus C3A3 all the way up to the last one. For any arbitrary c's, so the c sub I are scalars. I should say are any scalars. And so linear combinations of the columns are the column space. And so these columns, right, so the matrix is size m by n, right, and so m is the size of the columns. Like each individual column is m by 1, that means, right? Right, just to be clear, they're m by 1. And so that means Theorem 3 applies right away, right? So the column space of an m by n matrix is a subspace of Rm. And so again, Rm tells us the size of the columns. I should have just written that over here. And so that means we're talking about Rm when we're talking about the columns, and it turns out it's also a subspace. Now this one, we could also go through the definition and show that go through the definition of a subspace, which I've just shown you right here, to show that the column space is a subspace as well. But the other cool thing we could do is use what's on the next page of this, which is Theorem 1. And so Theorem 1 says, if we've got a bunch of vectors in a vector space, then the span of those vectors is a subspace. And so let me write that down right here, and then we can see how that applies right here. So Theorem 1 says that if we have a bunch of vectors, that should be VP. If we have a bunch of vectors in a vector space, then the span of those vectors is a subspace. So I'm just copying down column 1, or Theorem 1. And so that's exactly what we have here, right? We have vectors in Rm. Rm is a vector space, right? The columns are in that vector space. And so we've got a bunch of columns, and the column space is just the span of those things. And so it's literally an application of exactly what's being said there, right? So since A1 to AN, so the columns of A, the columns are vectors in Rm, which is a vector space. So that means then this implies that the column space of A is also is a subspace, because that equals the span of those vectors. So that's a subspace. So we can just refer to Theorem 1 from section 4.1 to sort of prove this theorem, just by saying, hey, look, we've got a bunch of vectors, like the columns are in Rm, that's a vector space, and the column space is just the span of those things. So it's literally an application just directly of that theorem. All right, cool. So now that we kind of know what the column space and the null space are, really common questions that you see are, well, you know, is this vector in the null space or the column space, or what is a, you know, what's a basis for elements in the column space or the null space? You know, what size are the vectors in these spaces, etc. And if we have a good understanding of like what's going on and how these things work, it's really not that tough of a problem. And so that's what's sort of on the next page here and how we want to finish this off. It can be confusing though, because these things are very similar, right? The null space and the column space are kind of similar, but very different as well. Okay, so we're going to be talking about this matrix A, and we're going to answer all these various questions about them, right? We'll find a non-zero vector in both spaces. We'll determine whether or not these vectors are in the space. But the first thing we're going to do is talk about the size of the vectors in each space. Okay, so A, here's A. It's a 2 by 4 matrix. Right? There's 2 rows and 4 columns. And so columns, the column space, are just linear combinations of the columns. And so that means the 2 tells you how big things are in the column space. Right? So the 2 here is going to tell us the size of vectors in the column space. Because it tells you how big the columns are, right? And then the 4, then, this is how big things are that you multiply by A. And the null space are things you multiply by A. And so the 4 tells you how big things are in the null space. And what we saw on the last couple pages was that the column space is a subspace of the range, and the null space is a subset of the domain. So I just want to add that note as well. So column space of A is a subspace of the range of A. Right, so 2 tells you how big things are in the range. And then the null space is a subset of the domain. Subspace, excuse me. Right, so one of these things is in the domain, the other thing is sort of like in the range, and so we're trying to think about, trying to differentiate the two and make sense of them, right? Okay, and so that means if we're trying to think about what size are the vectors in each one, I mean, we've kind of already done that right here, but I want to just reiterate that one more time and make it a little more clear if it's not clear already. And so, you know, if we have a value x and it's in the null space, then that means that you should be able to multiply it by A and get the 0 vector, right? And so that means x is in the null space, A is 2 by 4, and so that means x needs to be a 4 by 1 in order to multiply A in the first place, right? We need those inner dimensions to match up. And so if we know that we need to multiply vectors by A to be in the null space, you know, the second dimension obviously tells you how big they are, right? So this implies that vectors in the null space of A are 4 by 1. Okay. And then the column space are just the size of the columns, right? So the column space of A is the span of each one of these individual columns. So it's going to be the span of 1, 0, 2, 1, 4, 3, 0, minus 2. And so we're going to do linear combinations of those things. Right? And so we pick any C1, C2, C3, and C4 to be a column in the column space, or vector in the column space. And so we're adding together 2 by 1s, and so the vectors in the column space are 2 by 1s. So I really hope by the end of this, you know, what I've said at the top of the page here and what I've said right here, we have a good understanding of the size of the vectors in each one of those spaces. Just going to pause for 1 second here and let you finish writing that down. Okay. If we want to find vectors in the space, we have to do different things, right? So I'm going to slide this up just a tad here, and we can kind of use this to learn this and this to this, right? So, the column space is the easy one to do here. If you want to find a non-zero vector in the column space, you just need to do any linear combination of the columns. So you literally just pick C1, C2, C3, and C4 in this equation right here, and that's going to be a vector in the column space. And so if you want to find a vector in the column space, you can choose any C1, C2, C3, and C4 above, so right there. And so let's just pick some. So let's do like C1 equals C2, which is 0, and let's let C3 equal C4, which is 1. Literally any ones will work, but this is just making these two 0, and so then we're just going to add together those two. And so then we'd have 0 plus 0 plus 4, 3 plus 0 minus 2. And so we just add those two things together, and we would get 4, 1. And so this vector is in the column space because it's some linear combination of the columns. So if you want to find a vector in the column space, very easy. Just add together some combination of the columns. A vector in the null space is a little bit more challenging because if something's in the null space, it satisfies ax equals 0. And so that means we need to solve this equation, ax equals 0. It's not too hard, but it does involve like row reducing, for example, right? And so to find something, a non-zero vector in null space, we would want to solve ax equals 0. And we know how to do that, right? You just put the two things in an augmented matrix, you row reduce, you're going to have a free variable more than likely, and then you just choose a value for the free variable. And so here I am putting the two, I'm going to solve this system. So I'm going to put them in an augmented matrix, and that should be a 2. And with 0, of course. And then you row reduce, so RREF. I used a calculator ahead of time, and I got this reduced matrix. 1, 0, 0, 1, minus 2, 4, 3, minus 2, 0, 0. And so again, you can go back and look in chapter or section 1.5 if you want some reminders about how to solve homogeneous systems and everything. But like when we're looking at this, I've got a pivot in the first row, pivot in the second row, and so that means x3 and x4 are both free variables. And so that means x3 and x4 are going to be in my answer. Right? And so when you write down this answer, you get the following. The solution to this thing is going to be x equals, you're going to get, again, x3 and x4 in your solution. So you're going to get 2 minus 3, 1, 0 in terms of x3, plus minus 4, 2, 0, 1, x4. This is what's, as a quick reminder, this is called parametric vector solution. Parametric. There's the parametric solution for the null space. All right, so we solved ax equal to 0. This is our solution. It's got the free variables, and so you can pick any values for the free variables, and that'll be a specific solution, right? And so for a specific solution, right, because the question is find a non-zero vector. So we need to pick some numbers there to get one. So for a specific solution in the null space, simply choose values for x3 and x4. For example, if we let x3 equal x4 equals 1, so we just add the two vectors together, then that's going to be in the null space. Then minus 2, minus 1, 1, 1 is in the null space. And the idea is if this is the vector u, let's call it, then a times u equals 0. And you can double check that, right? Like you could take this vector, multiply it by a, the original a, and you should get 0, 0. Okay, so finding something in the null space is a little bit more challenging because you have to solve a system. Finding something in the column space is pretty easy because you just have to add together some combination of the columns. The sort of the difficulty switches when you want to see whether or not something is in the space. So for the last problems, it's easy to show something's in the null space. It takes a little more work to show something's in the column space. Right? So it's easy to show something's in the null space because you just want to see if you can multiply that by a and get 0. So see if a times v equals 0. That's how you just check that. So it's a very straightforward just matrix multiplication, right? This one's a little more challenging because if u is in the column space, then that means that you should be able to do some linear combination of the columns and get this value. And so that requires you to solve a system, because if u is in the column space, let me write this down. So if u is in the column space, then that means u is a linear combination of the columns. And so for some constant c, so some one, oh, and there's only 4 of them here, so it's not, let me just write those all out. So it's not up to Cn, it's C1, C2, C3, C4. For some C1, C2, C3, C4. Right, so if u is in the column space, then it's a linear combination of the columns, the 4 columns. And so that means we want to solve the system. You want to see if the system AC equals u has a solution. And so we're going to have to put the matrix A in a system with u and see if it has a solution. All right, so we're going to want to do this. Let me line these up a little better. That should go into the 4. Right, so here I am putting A. I'm trying to see whether AC equals U. So again, null space, it's easy to see if something's in the null space, just multiply it by A. If you want to see if something's in the column space, you put A in a matrix with that vector and see if there's a solution. So let me just finish this one since we've gotten pretty deep into it. Let's just reduce this one, RREF, and see if there's a solution. When I reduce this, I got this. Again, I just did this ahead of time on my calculator, and I got that row reduced matrix. And without even seeing what the solution is, I see there's going to be a solution, right? So this is a consistent matrix. You don't have something that says 0 equals not 0. And so there is a solution to AC equals U, right? So this is a consistent matrix. There's no 0 equals not 0. Thus, a solution exists. I don't know what it is, but I know it exists because we've got a consistent matrix. And so that means that 17.4 is in the column space. If we want to know the linear combination of the columns that give you 17.4, we would need to solve the system and get some values. But just seeing that there is a solution to the system is enough to say that it is in the column space. Let's just wrap this up with looking at the last one here. And so if V is in the null space, we should be able to multiply it by A and get 0. And so let's just see if that's true. So when we multiply A times V, it looks like this. So we take the matrix A, we multiply it by V, 2 minus 3, 1, 0. And you multiply each entry in the first row by each entry in the column, and then you add them together. Each entry in the second row multiplies each entry in the column, and so we'd get this then. Right? The 2 multiplies the 1, the 3 multiplies the -2, or the -3 multiplies the 2. We got 4 times 1, 0 times 0. And then we have 2 times 0, negative 3 times 1, 3 times 1, 0 times 0. And we see, when we add up the rows, we get 0, 0. And so V is in the null space because when you multiply it by A, you get the 0 matrix, right? So since AV equals 0, V is in the null space of A. And so, as a quick reminder, we did this section after subspaces because the null space and the column space are both subspaces of the domain and range. And depending on what the question is, they have varying levels of difficulty to figure out the answer, basically, is what I'm trying to say here. So what I'm trying to say is, if you want to see if a non-zero vector is in the null space, it takes a little bit of work. If you want to see a non-zero vector in column space, it's fairly straightforward. The opposite's true with the bottom ones. If you want to see if something is in the null space, it's easy. If you want to see if something is in the column space, it takes a little bit of work. And so that's what's summarized on the last page here. This last page isn't new material. It's basically just summarizing everything about null space and column space because, again, they're very similar, but they're also very different. And so it's easy to get them confused. It's easy to not be sure about how you answer some of these questions. And so these things sort of just contrast the two things that are going on. So like it says A is m by n, right? And so null space is a subspace of Rn, right? Column space is a subspace of Rm. So that tells you the dimensions and how it relates to each one. If you want it takes time to find a vector in the null space. It's easy to find a vector in the column space, right? A typical vector in the null space has this property. A typical vector in the column space means that AX equals V is consistent. So basically, it just summarizes the similarities and differences between the two of them. So hopefully when you're working on these things, or more importantly, when you're studying for a test, like I think these relationships, if they're clear in your mind, it'll be very, very helpful on tests and things like that. Okay, I'm going to stop here with that. Thank you very much.